Across the vast ocean of space, humanity has always reached out with curiosity, building instruments that extend our senses far beyond the limits of our eyes. From the glowing heart of our own Milky Way to the faint red light of galaxies born when the universe was still young, each new telescope has been a step further into the unknown. Today, we stand at a moment unlike any before, with the most powerful observatories ever created working together to peel back the layers of cosmic history. This is not simply a story of machines, but of the people and the dreams that made them real. In this journey, we will travel from the golden mirrors of the James Webb Space Telescope, capable of capturing light that has crossed billions of years, to the legendary Hubble, whose images have reshaped our understanding of the cosmos. We will venture to the frozen edge of the Kuiper Belt, follow the Voyagers as they drift through interstellar space, and explore bold ideas about the very shape and fate of the universe. Along the way, we will confront mysteries like the dark flow and witness how each discovery changes the questions we ask. 70 minutes from now, you will have crossed a landscape of stars, planets, and galaxies, some familiar and others never seen before. You will see how human ingenuity has transformed fragile dreams into instruments of breathtaking precision, and how each image they return is a fragment of a greater story. This is an invitation to leave behind the boundaries of Earth, to drift beyond the known, and to glimpse, for a moment, the endless frontier. Welcome to this voyage through space and time. The James Webb Space Telescope is not merely another step forward in astronomy. It is the single most ambitious space observatory ever built, the culmination of decades of design, engineering, and human persistence. Conceived in the 1990s, it was imagined as the successor to the Hubble Space Telescope, yet it quickly became something far more. Its purpose is nothing less than to look deeper into space and further back in time than any instrument before it, capturing light that has traveled across the universe for almost its entire existence. The scientific mission of this observatory is as ambitious as its engineering. It is designed to study the atmospheres of planets around distant stars, searching for chemical signatures that may hint at life. It will peer through thick clouds of gas and dust to witness the birth of new stars, and it will examine the faint light of the very first galaxies, formed when the universe was only a fraction of its present age. To do this, it operates entirely in the infrared spectrum, the only range of light capable of revealing these earliest and most hidden chapters of cosmic history. Observing in infrared presents its own challenges. The telescope must be kept colder than 100 degrees above absolute zero to prevent its own heat from drowning out the faint signals it seeks. This is why it orbits far from Earth at a position known as the second Lagrange point, about 1.5 million kilometers away. There, shielded from direct sunlight and protected by its vast sun shield, it can maintain the stability and frigid temperatures necessary for its sensitive instruments to function at their peak. The path to this point was neither short nor easy. Originally expected to cost a fraction of its final budget and launch in the first decade of the 2000s, the telescope endured years of delays and redesigns. Each of its 300 potential failure points had to be resolved before launch, for in the vacuum of space, there is no possibility of repair by astronauts. Every mechanism, from the unfolding of the mirror to the tensioning of the sun shield, had to work flawlessly the first time. When it finally launched in December of the year 2021, the world watched with anticipation. Over the following weeks, it performed a sequence of deployments and calibrations with near perfection. The sun shield unfurled, the mirror wings extended, and the instruments cooled to their operating temperatures. Each milestone was a triumph, bringing the telescope closer to opening its golden eye upon the cosmos. By mid-year, it began returning its first images, and they were nothing short of astonishing. Compared to Hubble, the James Webb Space Telescope sees the universe in a different light. Hubble excels in the visible and ultraviolet spectrum, capturing vibrant colors and fine details, but it struggles to pierce through cosmic dust and to detect the reddened light of the most distant galaxies. Webb's infrared vision complements this beautifully, revealing structures and phenomena that Hubble cannot see, while Hubble continues to provide views in wavelengths that Webb cannot capture. Together, they form a partnership unlike any in the history of astronomy. With its unparalleled sensitivity, Webb can detect the light of galaxies whose glow has been stretched into the infrared by the expansion of space itself. It can uncover the hidden nurseries where stars ignite from collapsing clouds of dust, and it can study the chemical fingerprints in the atmospheres of exoplanets, identifying gases such as water vapor, methane, and carbon dioxide. These capabilities open the possibility of discovering worlds with conditions that might one day be found to support life. Every image and every spectrum returned by Webb adds to a collective understanding of our place in the universe. It reminds us that the light reaching its mirror began its journey long before Earth even formed, crossing the cosmos to be captured by a machine built by a species just learning to stretch its reach among the stars. The James Webb Space Telescope is not simply a tool. It is a statement of intent, a declaration that humanity will continue to explore, to seek, and to learn. As we begin to explore the discoveries already made possible by this remarkable observatory, we step into a new chapter of astronomical history. In the coming years, its data will rewrite textbooks, inspire new theories, and perhaps even reveal that we are not alone. The Golden Mirror now watches over a universe vast and ancient, and its gaze will carry us further into that endless expanse than we have ever gone before. The images captured by the James Webb Space Telescope are more than breathtaking photographs. They are windows into epochs and places that human eyes have never seen. Each frame is a combination of extraordinary engineering, patient observation, and the deep physics of light traveling across unimaginable distances. What you are about to see are not artistic impressions, but real portraits of the universe, rendered in detail that was once thought impossible. These images are both scientific records and works of natural art, revealing the beauty and complexity of creation itself. Through the golden mirror of Webb, light that began its journey billions of years ago is finally collected, split into its colors, and transformed into information. In every image lies a story of stars being born, of others dying, of galaxies colliding, and of cosmic structures that stretch across light years. These photographs are not merely visual, they are maps of time, chemistry, and gravity. They allow us to peer past the veils of dust that have long obscured our view, to witness moments in cosmic history as if they were unfolding right now. One of Webb's earliest gifts to humanity is the portrait of the cosmic cliffs, a section of the Carina Nebula located about 7,600 light-years from Earth. What appears to be a jagged mountain range is in fact a vast wall of gas and dust, its peaks towering roughly 7 light-years high. This edge marks the boundary between a hollow cavity carved out by stellar winds from massive young stars, and the denser material beyond, where new stars are taking shape. The true wonder of this image is in what Webb reveals beneath the surface. In visible light, these regions are cloaked in shadow by thick dust. But Webb's infrared vision cuts through the gloom, exposing embryonic stars still wrapped in their natal clouds. The intricate textures and glowing edges speak of the constant interplay between radiation, gravity, and turbulence. This is a stellar nursery in action, offering clues to the stages of star formation that have shaped countless suns, including our own, across the history of the galaxy. From the drama of stellar birth, we move to the quiet grandeur of a star's final act. The Southern Ring Nebula, about 2,000 light-years away, is a shell of gas and dust expelled by a dying star. Despite its name, it has nothing to do with planets. Early astronomers simply thought its rounded shape resembled them. In the heart of the nebula lies not one star, but two, locked in a gravitational dance. One is near the end of its life, the other still shining steadily, and together they sculpt the patterns we see. Webb's dual views, one from the near-infrared camera and the other from the mid-infrared instrument, peel away the layers of gas and dust to show structures never before seen. The delicate rings and filaments are rich in elements that will one day seed future generations of stars and planets. Compared to earlier images, Webb reveals the cool, dusty regions with remarkable clarity, tracing the flow of material as it drifts outward into space. In these glowing remnants, we see both the ending of a star and the beginning of new cosmic possibilities. In the Large Magellanic Cloud, a small companion galaxy to our own, lies a region known as the Tarantula Nebula. Spanning hundreds of light-years, it is one of the most active star-forming regions in the local group of galaxies, lying about 161,000 light-years from Earth. Its name comes from its spidery filaments of gas, stretching out like legs across the cosmic web. For astronomers, this nebula is a living laboratory, echoing the intense star formation that once took place throughout the early universe. Webb's instruments pierce the bright haze to uncover thousands of young stars, some only just igniting their nuclear furnaces. The nebula's dense knots of dust and gas are shaped by fierce stellar winds and radiation, creating cavities, pillars, and arcs that change over time. By studying regions like this, scientists can compare present-day star formation to the era known as the cosmic noon, about 1 billion years after the Big Bang, when galaxies were at the height of their star-making activity. The Tarantula Nebula is a reminder that the cycle of creation continues even now, in our own cosmic neighborhood. Among Webb's most dramatic early images is the portrait of Stephan's quintet, a group of 5 galaxies locked in a complex gravitational dance. 4 of these galaxies are physically close and interacting, while the 5th lies much nearer to us, a foreground neighbor. Seen together, they form a cosmic stage where forces of unimaginable scale are at play. Streams of gas are being pulled from one galaxy to another, while vast regions glow under the compression of star-forming clouds. The detail revealed by Webb is unprecedented. Shock waves from galaxy collisions ripple through interstellar space, heating gas to extreme temperatures and triggering bursts of star birth. The mid-infrared view uncovers dust structures curling between galaxies, tracing the flow of matter like smoke carried by a cosmic wind. These interactions are a glimpse of what will one day happen between our Milky Way and the Andromeda Galaxy, showing how galactic mergers shape the large-scale structure of the universe over billions of years. Perhaps the most astonishing achievement in Webb's first release was the image known as the first deep field. At first glance, it appears as a scatter of countless points of light, but almost everyone is a galaxy, each containing billions of stars. The image covers an area of sky no larger than a grain of sand held at arm's length. Yet within that tiny patch, Webb captures a cosmic cityscape extending back nearly to the dawn of time. Some of the galaxies appear warped and stretched, their shapes distorted by a phenomenon called gravitational lensing. This occurs when the gravity of a massive cluster of galaxies bends and magnifies the light of far more distant objects behind it. In this way, Webb acts not only as a telescope, but also as a cosmic time machine, revealing galaxies that existed when the universe was less than 1 billion years old. The fact that such depth and clarity were achieved in less than a day of observation speaks to the extraordinary sensitivity of its instruments. Taken together, these early images from the James Webb Space Telescope are more than a demonstration of technology. They are a promise of discoveries yet to come. From the sculpted cliffs of stellar nurseries to the intricate shells of dying stars, from the tangled threads of galactic encounters to the faintest glimmers of the first galaxies, Webb's vision reaches across both space and time. Each frame deepens our understanding of how the cosmos grows, evolves, and renews itself. These images remind us that our universe is a place of constant transformation. Stars are born, live out their brilliant lives, and die, scattering the elements for the next generation. Galaxies merge and reshape, weaving the tapestry of cosmic history. And through it all, light travels vast distances, waiting patiently to be seen. With Webb now watching, humanity can witness these stories in unprecedented detail, turning distant mysteries into vivid, tangible realities that inspire both science and wonder. The James Webb Space Telescope was designed with a mission plan that stretches across decades of research, engineering, and strategic observation. Its primary goal is to study the universe in infrared light, allowing astronomers to see through cosmic dust, detect the faintest and most distant galaxies, and examine the atmospheres of planets around other stars. Over its initial years, Webb will follow a carefully prioritized list of scientific programs, each chosen to address fundamental questions about the origin, structure, and fate of the cosmos. From its vantage point at the second Lagrange point, Webb can maintain a stable temperature and unobstructed view of space. This position enables it to observe continuously, without the interruptions that affect telescopes in low Earth orbit. Its schedule is a balance between large-scale surveys and targeted studies. Some programs will map entire swaths of the sky in unprecedented detail, while others will focus on specific phenomena, such as the birth of stars in dense nebulae, or the slow death of ancient suns shedding their outer layers. A major part of Webb's activity will be devoted to studying exoplanets, the worlds orbiting other stars. By passing starlight through the thin atmospheres of these planets, Webb can detect the chemical signatures of gases such as water vapor, methane, and carbon dioxide. These observations may reveal environments that are potentially hospitable to life. Combined with data from other observatories, Webb's exoplanet studies will build a richer picture of how planetary systems form and evolve, and how common life-sustaining conditions might be in the galaxy. Another critical area of focus is the early universe. Webb will peer back to the first hundreds of millions of years after the Big Bang, capturing light from the first generation of galaxies. These observations will help scientists understand how the earliest structures assembled, how stars and black holes formed in those ancient systems, and how cosmic reionization transformed the universe from a dark, opaque place into the transparent cosmos we see today. By comparing galaxies across time, Webb will chart the story of growth on a cosmic scale. Webb's mid-infrared instruments will also explore the hidden processes of galaxy evolution. Dust, which obscures visible light, becomes luminous in the infrared, allowing Webb to study the engines of star formation inside otherwise opaque regions. These observations will connect the dramatic collisions of galaxies with the cycles of birth and death among their stars. By building a detailed understanding of these processes, astronomers can link the grand shapes of galaxies to the small-scale physics that governs their internal life. The mission's potential extends beyond its original goals. As history has shown with the Hubble Space Telescope, some of Webb's most important discoveries will likely be unplanned. Its unmatched sensitivity and resolution make it a tool for detecting rare, transient events, supernova explosions, cometary outbursts, or the unexpected flares of distant quasars. By responding quickly to such events, Webb can capture fleeting moments in the life of the universe, adding new chapters to the story of cosmic change. In the years to come, Webb will operate in close partnership with other observatories on the ground and in space. Together, they will form a global network for exploring the cosmos, each complementing the other's strengths. Webb's data will not remain locked away. It will be shared with the worldwide scientific community, sparking research in countless directions. Whether revealing the weather on a distant exoplanet, tracing the assembly of galaxies, or glimpsing the first light in the universe, Webb is poised to redefine our understanding of the cosmos. Long before the James Webb Space Telescope unfolded its golden mirrors, another pioneer had already changed the way humanity looked at the cosmos. Launched in the spring of 1990, the Hubble Space Telescope began its mission, orbiting above Earth's atmosphere, free from the distortions and limitations of ground-based observatories. With its clear and steady vision, Hubble opened a new era of astronomical exploration, turning faint smudges into detailed galaxies and revealing cosmic structures in stunning clarity. Hubble's journey was not without challenges. Soon after launch, a flaw in the main mirror left its images blurred, threatening to undermine the mission. But in one of the most remarkable feats of human ingenuity, astronauts aboard the space shuttle installed corrective optics during a servicing mission, giving Hubble the perfect eyesight it had been promised. This repair transformed the telescope into a scientific powerhouse, allowing it to capture images that would inspire generations. Over the decades, Hubble has contributed to nearly every field of astronomy. It measured the precise rate of expansion of the universe, refining the value of the Hubble constant and deepening the mystery of dark energy. It captured the birthplaces of stars inside glowing nebulae and documented the violent deaths of massive suns as they erupted into supernovae. By combining images taken over years, Hubble also tracked the slow motion of galaxies, revealing the gravitational dance that shapes the universe on the largest scales. Among Hubble's most celebrated achievements are its deep field images. By staring at a seemingly empty patch of sky for many days, the telescope revealed thousands of galaxies stretching back billions of years into the past. These deep fields showed that even the smallest and darkest corners of the sky are teeming with cosmic life, each point of light a vast system of stars. The images gave astronomers a direct view of galaxy formation and evolution across cosmic history, bridging the gap between the early universe and the present day. Hubble's instruments have also been a key tool in the search for exoplanets. By watching for the faint dimming of a star as a planet passes in front of it, and by studying the starlight that filters through planetary atmospheres, Hubble has detected water vapor and other molecules beyond our solar system. These findings have laid the groundwork for the more advanced surveys of the James Webb Space Telescope, proving that the universe holds worlds far more varied than those in our own planetary neighborhood. The telescope has played an equally important role in planetary science closer to home. Hubble has monitored storms raging across Jupiter, watched seasonal changes on Mars, and followed the shifting clouds of Neptune and Uranus. It has captured rare events, such as the impact of a comet into Jupiter's atmosphere, offering scientists a real-time laboratory for studying planetary dynamics. In doing so, Hubble has shown that space telescopes can be as valuable for studying our own solar system as they are for exploring the distant universe. Hubble's longevity is a testament to human dedication. Across 5 servicing missions, astronauts have repaired, upgraded, and extended the telescope's capabilities, ensuring it could continue to deliver groundbreaking science for decades. Even now, with Webb taking the spotlight, Hubble remains an essential partner, working in tandem to provide complementary views across different wavelengths of light. Together, they form a bridge between the discoveries of the past and the possibilities of the future, proving that in exploration, every chapter builds upon the last. Far beyond the orbit of Neptune lies a vast and mysterious region known as the Kuiper Belt. This distant expanse forms a kind of frozen frontier, stretching billions of kilometers from the Sun. It is filled with icy bodies, ancient remnants from the earliest days of the solar system. Unlike the rocky planets or the gas giants, the Kuiper Belt's inhabitants are pristine time capsules, preserving the conditions of a young sun surrounded by swirling clouds of dust and ice. The Kuiper Belt is not empty space. It is a busy neighborhood of comets, dwarf planets, and countless smaller icy fragments. Pluto, once considered the 9th planet, is its most famous resident, joined by other dwarf planets such as Eris, Haumea, and Makemake. These worlds are diverse in shape, color, and composition, some with thin atmospheres, others with unusual elongated forms, and many marked by ancient craters. Each object is a clue to how planets and moons formed over 4.5 billion years ago. This frozen frontier is also a source of many short-period comets, the ones that visit the inner solar system on orbits lasting only a few hundred years. These comets are thought to have originated as icy bodies in the Kuiper Belt, later nudged inward by gravitational encounters. When their orbits carry them close to the Sun, the heat causes their icy surfaces to vaporize, creating the glowing comas and tails we see from Earth. They are, in a sense, emissaries from the edge of the solar system. Exploration of the Kuiper Belt has only just begun. The most remarkable encounter to date came from NASA's New Horizons mission, which flew past Pluto in 2015, revealing a complex and active world with nitrogen glaciers, towering mountains of water ice, and an atmosphere that extends far into space. Later, New Horizons visited another Kuiper Belt object nicknamed Arakoth, a contact binary shaped like a snowman, showing scientists the untouched building blocks of planetary formation. Studying the Kuiper Belt is not only about understanding these distant bodies, but also about unlocking the history of the entire solar system. The arrangement, size, and composition of these objects offer evidence for the early migration of the giant planets. Jupiter and Saturn, in particular, are believed to have shifted their positions in the past, scattering smaller icy bodies outward to form the Kuiper Belt as we see it today. In this way, the belt is like a fossil record of planetary motion. The Kuiper Belt also raises tantalizing possibilities. Some astronomers suspect that a massive, unseen planet, often referred to as Planet 9, may be lurking far beyond Pluto, influencing the orbits of certain distant objects. If such a world exists, it could reshape our understanding of the solar system's architecture. Even without this hidden giant, the Kuiper Belt remains a dynamic and evolving frontier, its members slowly shifting and colliding over immense spans of time. In the coming decades, more missions may venture into this icy expanse. Improved telescopes, both on Earth and in space, will map its population in greater detail, while spacecraft could perform close flybys of multiple Kuiper Belt objects. Each new discovery will add to the tapestry of the solar system's story, connecting the cold, distant edge to the warm, familiar heart where Earth resides. The Kuiper Belt is not simply the outer boundary of our sun's reach. It is a reminder that the frontier is always expanding for those willing to seek it. In the final decades of the 20th century, when the Cold War still shaped the ambitions of nations and space exploration stood as a testament to human ingenuity, two small spacecraft were prepared for a journey unlike any before. They were named Voyager 1 and Voyager 2. Conceived during a time when the boundaries of the known solar system seemed vast, yet reachable, these twin emissaries were built not only to study the outer planets, but also to test the limits of human reach. Their mission was to venture farther than any machine had ever traveled. The Voyagers were designed to take advantage of a rare planetary alignment, an arrangement that occurs only once every 176 years. This alignment allowed for a grand tour of the giant planets, using their gravity to slingshot the spacecraft onward with minimal fuel. The vision was bold: to visit Jupiter, Saturn, Uranus, and Neptune in a single mission, gathering unprecedented images and measurements, and in the process writing a new chapter in the story of exploration. But the Voyagers were more than scientific instruments. They carried within them a message from Earth to any intelligent life they might one day encounter. This message, etched onto a golden record, was filled with sounds, images, and music from our world, a cultural time capsule cast into the cosmic ocean. It was a statement of hope, declaring that humanity, though small and young in the universe, sought to connect, to learn, and to be known across the stars. Voyager 2 was launched first, in August of 1977, aboard a Titan Centaur rocket from Cape Canaveral in Florida. Though named 2, its trajectory was slower, designed to reach all 4 giant planets in succession. Voyager 1 followed in September of the same year, taking a faster route that would carry it past Jupiter and Saturn before breaking away toward the outermost regions of the solar system. Their paths were carefully planned to maximize the gravitational assists that would speed them along. Both spacecraft carried a suite of sophisticated instruments: high-resolution cameras, magnetometers, plasma detectors, and radio science systems. They were powered by radioisotope thermoelectric generators, converting the heat from decaying plutonium into electricity. A steady source of power capable of sustaining them far from the sun. Every component was built with durability in mind, knowing that these machines would travel for decades through environments of radiation, dust, and extreme cold. The early phase of their journey was a test not only of engineering, but of human patience. Signals from the Voyagers, traveling at the speed of light, took many hours to reach Earth and return. Navigating the vastness of space required precision, measured in fractions of a degree, and even the smallest course correction had to be planned with care. As the months passed, the first images and data began to flow back, tantalizing glimpses of what lay ahead, and confirmation that the gamble of this mission was beginning to pay off. The first great destination for both Voyagers was Jupiter, the largest planet in the solar system. In the spring of 1979, Voyager 1 swept past, followed by Voyager 2 a few months later. The images they returned revealed the gas giant in stunning detail: vast cloud bands swirling in perpetual storms, lightning flashes illuminating the night side, and the Great Red Spot, a tempest large enough to swallow Earth. Jupiter was not merely a giant ball of gas. It was a dynamic, violent world, alive with motion and power. Among the most startling revelations came from Io, one of Jupiter's moons. The Voyagers discovered it was the most volcanically active body in the solar system, its surface dotted with erupting plumes that rose hundreds of kilometers into space. This activity was driven not by sunlight, but by tidal heating, the immense gravitational pull of Jupiter flexing and heating the moon's interior. The finding revolutionized planetary science, proving that moons could be geologically active far from the warmth of the sun. The spacecraft also brought back images of Europa, a moon with a smooth, bright surface crisscrossed by dark cracks and ridges. Scientists soon realized that beneath this icy shell might lie a vast ocean of liquid water, kept from freezing by heat from the moon's interior. The possibility of a subsurface ocean made Europa one of the most promising places to search for extraterrestrial life, a legacy of the Voyager's brief but transformative visit. In 1980, Voyager 1 reached Saturn, revealing its iconic rings in intricate detail. The spacecraft captured fine structures within the rings, narrow gaps, twisting waves, and mysterious clumps of material shaped by the gravity of small shepherd moons. Saturn's atmosphere was a tapestry of golden clouds, whipped into long linear storms by high-speed winds. The giant planet seemed at once serene from a distance and turbulent up close. Perhaps the most intriguing stop at Saturn was Titan, the largest of its moons. Voyager 1's instruments detected a dense atmosphere composed mostly of nitrogen, with traces of methane and other organic molecules. The haze was so thick that the surface could not be seen, but the discovery of such an atmosphere hinted at complex chemistry, the kind that might resemble the early Earth before life emerged. Titan would become a prime target for future missions. Voyager 2 alone continued on to Uranus in 1986, the first and only spacecraft to visit this ice giant. The planet's pale blue-green hue came from methane in its atmosphere, and it rotated on its side, its axis tilted almost 90 degrees. The flyby uncovered 10 new moons, several faint rings, and a magnetic field oddly offset from the planet's center. In the cold, dim light, nearly 3 billion kilometers from the Sun, Uranus was a strange and silent world. In 1989, Voyager 2 reached Neptune, the final planet in its grand tour. Here, it discovered the Great Dark Spot, a massive storm system as fierce as Jupiter's red spot, but short-lived. The spacecraft also encountered Triton, Neptune's largest moon, whose icy surface was marked by active geysers erupting nitrogen gas into the thin atmosphere. This was the coldest known place in the solar system, yet it was alive with unexpected energy. By the time the Voyagers had completed their planetary encounters, they had rewritten the textbooks. They revealed active volcanoes on distant moons, hidden oceans beneath icy crusts, atmospheres thick with organic compounds, and planetary systems more diverse than anyone had imagined. Each stop along their journey expanded the boundaries of what humanity knew, transforming the outer solar system from a collection of faint points of light into vibrant, complex worlds. Long after their encounters with the outer planets, the Voyagers continued their silent voyage outward, powered by the steady warmth of their nuclear generators. Decades passed, and the faint light of the Sun grew weaker until it was little more than a bright star in the distance. Beyond the orbits of the farthest worlds lay the heliopause, the invisible boundary where the Sun's influence ends and the vast interstellar medium begins. Crossing it would mean leaving the solar system behind and entering a new realm between the stars. In the year 2012, Voyager 1 became the first human-made object to cross that threshold, detecting a sudden shift in particle density and magnetic fields. 6 years later, Voyager 2 followed, carrying its own set of instruments into the interstellar dark. These crossings were not marked by fireworks or visible lines, but by quiet, decisive changes in the data, the telltale signs that the spacecraft had stepped into a place no human eyes had ever seen. From the moment they were launched, the Voyagers carried something more than cameras and sensors. Bolted to the side of each spacecraft was a gold-plated copper disc, engraved with a map of our place in the galaxy, and filled with the sounds and images of Earth. Known as the Golden Record, it was a greeting card to the cosmos, designed to survive for 1 billion years. Within its grooves were voices in 55 languages, music from across human history, and the sounds of wind, rain, birdsong, and laughter. The idea came from a team led by Carl Sagan, who imagined the record as a time capsule, a message in a bottle cast into the cosmic ocean. It spoke of our planet's beauty, our diversity, our yearning to connect. No one knows if the record will ever be found, but that was never the point. Its presence aboard the Voyagers stands as a quiet declaration that even as we reach outward into the void, we bring with us a piece of home, a reminder of who we are, and a hope that somewhere, someday, someone might listen. Today, both Voyagers continue to send faint whispers back to Earth, their signals taking over 18 hours to cross the immense gulf. The spacecraft are now so far from home that the sun appears no brighter than other stars in their sky. Their instruments still function, though power is carefully rationed as their generators slowly weaken. Engineers make difficult choices, shutting down one system after another to preserve the most vital sensors for as long as possible. It is expected that within the next decade, the Voyagers will fall silent. When their power finally fades, they will drift through interstellar space, still intact, still carrying the golden record, but without a voice to call home. Even then, their journey will continue. They will travel for millions of years, crossing the space between the stars, passing perhaps within a few light years of other suns, silent ambassadors from a small blue world that once dreamed of reaching them. There is something profoundly human about the Voyagers. They are machines, yes, but they carry our curiosity, our art, our science, and our hope. They remind us that exploration is not only about what we might find, but about who we become when we dare to venture into the unknown. Every bit of data they return, every image they captured, is a message that we are part of something far larger, and that the urge to explore is woven into what it means to be human. One day, long after our cities have crumbled and our languages have changed, the Voyagers will still be out there. Somewhere in the darkness, they will be carrying our story, a fragile spark of memory moving between the stars. Perhaps they will never be found. Or perhaps, in some distant future, another intelligence will hold the golden record and wonder about the beings who sent it. Either way, the Voyagers have already fulfilled their greatest mission, to remind us that, in the vastness of the universe, we dared to say, we were here. When we imagine the universe, our minds often picture a vast sphere stretching endlessly in all directions. But the question of its actual shape is far more complex. Cosmologists have spent decades trying to understand whether space is curved like the surface of a sphere, flat like an endless sheet, or saddle-shaped, bending outward in one dimension while curving inward in another. The shape of the universe is not just a matter of geometry. It tells us about its origin, its contents, and its ultimate fate. Einstein's theory of general relativity links the curvature of space to the amount of matter and energy it contains. If the density of the universe is high, gravity bends space into a closed shape, like the surface of a ball, where traveling far enough in one direction could bring you back to your starting point. If the density is low, space could be open, stretching forever with no return. In between lies the flat universe, balanced perfectly, where parallel lines stay parallel for eternity. Modern observations, especially of the cosmic microwave background, the faint afterglow of the Big Bang, have given us remarkable clues. Measurements suggest that the universe is astonishingly close to flat, with any curvature so slight it is beyond our current ability to detect. This flatness aligns with the predictions of cosmic inflation, the theory that space expanded exponentially in the earliest fraction of a second after the Big Bang, smoothing out any irregularities. But even if the universe is flat, that does not mean it is infinite. Space could be finite yet unbounded, like the surface of a cylinder or a torus, shapes that repeat themselves without edges. In such a cosmos, traveling far enough might bring you back to where you began, not because space curves inward, but because it connects to itself in a higher dimensional way. The very idea challenges our everyday sense of geometry and distance. The shape of the universe also affects its destiny. A closed universe might one day stop expanding and collapse in a big crunch, while an open or flat universe will likely expand forever, growing colder and emptier as the stars fade. The presence of dark energy complicates this picture further, accelerating the expansion in ways that could lead to a future far stranger than we can now imagine. Ultimately, the question of the universe's shape is as much philosophical as it is scientific. It reminds us that our senses evolved for the scale of trees, rivers, and mountains, not for the vast canvas of the cosmos. Yet, here we are, tiny beings on a small world, measuring the curvature of space itself. In seeking the universe's shape, we are also tracing the outline of our own curiosity, drawing the first lines in a map whose edges we may never see. As our journey through the cosmos draws to a close, we are left with a sense of both humility and wonder. From the delicate structures of nebulae captured by the James Webb Space Telescope to the silent voyage of the Voyagers beyond the sun's reach, each story has been a reminder that the universe is not a static backdrop, but a living, evolving stage. We have glimpsed its beauty, measured its distances, and traced its history back to the first moments after time began. The vastness of the universe can feel overwhelming. Its scale stretches beyond our imagination, and its timescales make our lifetimes seem like fleeting sparks. Yet in that immensity lies a powerful truth, that we are part of it. The atoms in our bodies were forged in the hearts of ancient stars, scattered across space by explosions long before Earth formed. Every breath we take is a quiet echo of cosmic events that shaped the galaxies themselves. Exploration has always been more than a scientific pursuit. It is an act of hope, a statement that knowledge is worth seeking even when answers are incomplete. The instruments we send into space, the telescopes we raise to the skies, and the data we collect are all extensions of our curiosity. They bridge the gap between what we know and what we still dream to understand, carrying our questions into the deep unknown. But with knowledge comes responsibility. As we learn more about our universe, we also gain perspective on the fragile world we inhabit. From space, Earth appears as a small, bright sphere suspended in darkness, its thin atmosphere the only shield protecting life. This view reminds us that, despite our divisions, we share a single home. The cosmos may be vast, but it is not endless in what it offers us, and what it offers can be lost. The message carried through all these discoveries is simple yet profound. The universe is not separate from us. We are woven into its fabric. Our stories, our art, our science, and our dreams are all part of the same great unfolding. Whether we look to the past to see where we came from or to the future to imagine where we might go, the act of looking connects us to each other, to our planet, and to the stars. So, as we end this journey, let us remember that the cosmos is not only something to observe, but something to belong to. Every image captured, every measurement taken, and every mission launched is a way of saying to the universe, we are here, we are learning, and we are reaching out. And perhaps, in some distant place and time, that message will be heard, and our small voice will join the eternal chorus of the stars. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.